Right. Thank you very much for your time today. So we want to continue with conversations on important laws and theorems under probability. Right. We've had this series of conversations for the past, I think, two meetings, and we in the previous session considered the idea of conditionality of probabilities, and that helped us to define the general and the special multiplicative laws. And we looked at their extensions, their corollaries, right? How we can extend from just two event scenarios to three event scenarios and n event scenarios in generality. What we want to consider today is the idea of total probability, and we would leverage this concept to discuss another important principle or theorem, which we call the Bayesian theorem. And we would put these two together to discuss some other important theorems and laws of probability. So we will begin with the total probability law, or in other texts, the law of total probability, right? So we'll take a formalized theorem to sort of introduce this law. But let me just start by saying that the addition and multiplication laws are the basic tools of probability. And the application of these laws may be demonstrated in what we're coming to study, which is the total probability law, which we also call the law of incompatible and exhaustive causes, right? In other literature, that's what you would come about. So let's take a formalized definition for what this total probability law is all about. So this is theorem right? So consider right? Consider, let's say, some AIs. So A1, A2, all the way to some AN. Okay, now let these form what we call a partition. So consider A1, A2, AN forming a partition. Partition of the sample space. All right. Then for any events, and let's call that B. Okay, for any event B, which is a subset of the sample space, and the probability of B is not zero, okay, then the following principle holds. So it holds that then we can find an expression for the probability of B, right? So the probability of B is given by the probability of A1 intersection B added to the probability of A2 intersection B, all right, plus all the way to the probability of AN intersection B. But of course, a more elegant way to write this is to say that we're taking the successive, the additions, okay, of the various probabilities. So we can write AI intersection B, okay, and we're summing them up. We're summing them from I starting from 1 all the way to I ending at N. Okay, so before we consider the proof for this theorem, let's spend some time to digest this properly, right? We're saying that, and probably I can do this with, with some visual just to help you appreciate it. So let's just write the proof out here. So let's start with this diagram. All right, so let me just draw this out. So I'm going to draw my entire sample space. Okay, so we can say that let us partition. So consider the following. Partition. Okay, of the sample space. And I want to do the following. So the sample space is the entire collection, right? The whole rectangle. Because every possible occurrence must happen within the rectangle, right? I think my rectangle is tilted a bit, but hopefully you just get the idea. Right. So this is my omega. Right. Good. Now in here, you see, I keep talking about the idea of a partition, right? So I am partitioning my omega into some A1, A2, and A3, and A4, all the way to AN. So when we talk about a partition, right, there are two things that you need to keep in mind. For a partition to happen, we're looking at mutual exclusivity and then collective exhaustivity, right? So let me just write that out here. I can put that in just red, okay, just so you know it's an important note. So when we say a partition, think about these two things. Mutually exclusive and then collectively exhaustive. Right. So mutually exclusive, as you know, it simply means that they don't have overlaps. They don't overlap, or it's not possible for the two events or the three events to occur at the same time. Okay. Now, collective exhaustivity simply means that when we take the unions of those various events, they need to give us back the entire sample space. All right. So just think of it this way. Let's suppose that you have a house, right? And just to make the example a very simple one, we just have a simple one. I mean, just a basic house, right? Now, a basic house, you have some important compartments, right? You would have what, a kitchen, you would have a living room, and then let's say you have a bedroom. Okay, let's just say this is just a basic house. So you know that the kitchen and the living room don't have overlaps, right? There's clearly a kitchen, and then you have a door to show that this is the boundary, right? There is clearly also a boundary between the living room and then the bedroom, and vice versa, right? So once you move from the bedroom, you get out of the door, you know that you're going to, depending on the configuration of the house, either you're going to the kitchen or you're going to the living room, right? So that is number one. They are mutually exclusive, meaning that your kitchen and then your bedroom don't have any overlaps, right? And at the same time, the living room and your bedroom do not have overlaps. Okay. And at the same time, your living room and your kitchen do not have overlaps, right? So that's mutually exclusive. Then if we say collective exhaustivity, or to be collectively exhaustive, it means that if I take the union of the kitchen space with the living room space, and I unionize that to with the bedroom space, what do I get? I need to get back the entire house. You understand? If, let's say, the house has a garage, then it means that now we have four spaces in the house, right? We have a kitchen, a living room, a bedroom, and then what? A garage. And all these are mutually exclusive. Okay, good. Now, at the same time, if I take the unions, I take the union of the kitchen, the living room, the bedroom, and then the garage, I need to get back what? The whole house. So that's the idea of a partition, right? So when you think about a partition, the two characteristics of a partition is, or are, mutually exclusive and then collectively exhaustive. All right. Now it's important because you can have an instance where they are mutually exclusive, but they are not collectively exhaustive. All right. So once again, let's take the house scenario. If you have a house that's made up of a bedroom, a living room, a kitchen, and then let's say a porch, for example, right? So there are four different spaces. Now, if you only consider just two of the spaces, and the spaces here represent events, right? So if you consider, say, the living room and then the bedroom, well, of course, it's true. The living room and the bedroom are mutually exclusive because they do not overlap. But if I just take the living room union the bedroom, it will not give me the whole house. There will still be other spaces that I haven't accounted for, right? So we only use the term partition when the property of mutual exclusivity holds, and at the same time, collective exhaustivity is also satisfied. All right. So just keep these in mind. So now back to our proof for total probability. So we're talking about what? Some partitions of this entire sample space. So let's do the partitioning here. This could be let's go back to the green. Yes. So this could be my So I'm just partitioning them. So let's call this A1. This is my first space. Okay, this is my A1. Let's say, let me draw them properly. Okay. So let's call this A1. Let's also maybe call this A2. All right. Then, so I can do several such partitions. All right. I can do several such partitions. All right. So let me just say that this is A1, A2. And then let's say I could partition several. Okay. I can make several partitions. So let me just use the ellipsis because it goes on and on and on, all the way up to, let's say this is our AN. Okay, I'm using this because if I say I really want to partition the sample space, I would end up having very small, minute, almost microscopic spacings, and I don't want to do that. So this is A1, this is A2. We could also have A3, A4, somewhere A5, all the way to AN, where N could be 1,000, several events, right? Good. And so this is A1, A2. Maybe let me just fix the A3 somewhere here. Then we have all the A, and so on and so forth, right? Okay, so that's it. So consider these partitions. We've done that. Then now the next thing we need to define is for any event B, and B is a subset of the sample space, okay? So I need to draw the B very well because it covers the region. So let me use a different color for the B. All right. And let me call this B. Right. So now we have a partition of the sample space and we've defined an event B. Okay. And B satisfies these conditions, right? B is within you see, because I said B is a subset or could be the sample space. So I need to draw it in such a way that it shares some boundary with all of the other partitions. Because keep in mind, the partitions are called partitions because if you take their union, they would give you what? The entire sample space. And so if we have another event B, which may also be the sample space, and I need to draw it in such a way that it represents this claim. All right. So that's how come we're drawing the B this way. Good. So given this scenario, right, let's now establish the proof. So it means that my sample space, okay, it consists of events A1, A2, all the way to AN. Okay. And clearly, we see that these events, okay, they are pairwise mutually exclusive. Okay, so they are all mutually exclusive and they are collectively exhaustive. In other words, clearly, A1 shares no area with A2. A1 doesn't share any area with A3. A2 doesn't share any area with AN, and so on and so forth. So they are mutually exclusive. And at the same time, if I take A1 union A2, union A3, union A4, union A5, all the way to union AN, what do I get? I get the whole sample space back. All right. So just for purposes of learning, right, and for instruction for that matter. So I just want to write, so observe that the events AI, or let me say that the AIs all right, are mutually exclusive. Okay. But I'm being more specific. They are pairwise mutually exclusive, meaning that if you take any two in turns, or you could also say that they are pairwise disjoint. All right. They are pairwise disjoint. They are pairwise disjoint. And their union is omega, right? So equivalently, what we are just trying to say is that if you take any of the AIs, right? So they are pairwise disjoint, meaning that AI intersection AG would always be the empty set, all right, for I not equal to J, all right, and the union of the AIs would give you what? So this is it, right? So they are pairwise disjoint, and then they are collectively exhaustive. Now, let's go back to the diagram, right? And that we can proceed from there. So now, again, if we take a look at this particular visual, this particular figure, okay, we can see that the B, this whole B, right? Just look at it properly. Just the area bounded by the red. Okay, how can we find B, or in which other way can we write out the B? Do we see that the B is essentially this portion, right? Look at it closely. If I want to get the whole circle back, right, I can take the intersection of A1 and the B. That will give me the small portion. I can take the intersection of A2 and the B. That will give me the small portion. I can take the intersection of A3 and the B. That'll give me the small portion. I can take the intersection of A4 and the B. That'll give me this portion, and so on and so forth, till I get to the intersection of the AN and the B. That will give me this small portion. By the time I take all those little intersections and I put all of them together. When I say I put all of them together, I mean when I unionize all those little intersections, they would necessarily give me back the whole circle. Okay? Therefore, this means that so notes from the figure, right? So from the above figure, that the B, the whole region, the whole circle or oval, is essentially taking all the AIs, intersecting them with the B. Okay, this alone will give you those small portions. And if we take the union of these intersections, everything will give us back the B. All right. Good. Now, keep in mind, so I've written this already. Since the AIs are pairwise disjoint, okay, meaning that if you take any two, let's say A1 intersection A2, it will give you an empty set. If you take A1 intersection, let's say A5, it will be empty. If you take A3 intersection A10, it will be empty, right? So they are pairwise disjoint. So since this holds, right? So let me just repeat it. Since AI intersection AJ is empty, okay, for I not equal to J, then we can also argue that if you take the same statement, right, then it means that every AI intersection B, if you intersect it with another AJ intersection B, there should be an empty set. Let's go back to the figure to explain this, right? The pairwise disjoint idea simply says that A1 intersection A2 is empty, A1 intersection A3 is empty, and so on and so forth. I think that's clear, right? So now we're saying that if you take these little intersections, let me color them, right? Look at it closely. So maybe let me use a blue here. So this is it. A1 intersection B, okay, versus A2 intersection B. etc., all the way to AN intersection B. And then this part also, right? The point that we're making is, look at this region, A1 intersection B. That region does not overlap with A2 intersection B. They are mutually exclusive regions, right? If you take, let's say, A3 intersection B or A4 intersection B, this region, it doesn't overlap with AN intersection B, right? So visually, we can establish that claim, but we're just making an algebraic inference here that if AI intersection AJ is equal to the empty set, then it means that if we intersect the AIs and the AJs with a common event, it would still hold that they are empty. And the proof is given visually, as I've just told you about, right? Good. So since this is that, it holds that we can also argue that then okay, so we can say that AI intersection B, right, which is the blue regions. Okay, any blue region intersection any other blue region would always be empty, right? For when we say for I is not equal to J, we simply mean that, for example, if you take A1 intersection A2, obviously 1 is not equal to 2, right? If you take A2 intersection A5, obviously 2 is not equal to 5, right? So it's just to show that there are different regions that we are operating upon. All right, good. So now, what is the end goal? The end goal is to arrive at, let's take a look at the theorem again, right? So there is a particular theorem that we've looked at in the past, right? That can help us to arrive at that intended destination. All right. So when you take a look at this very, very closely, okay, you'll see that we can make some we can make some deductions here, right? You recall there was a particular theorem which is supposed to be I think it's the special additive law, right? The special additive law. We looked at the corollary, if you recall, right? And the corollary says that for a set of mutually exclusive events, AI, where I runs from 1 all the way to 2, right? The probability of the occurrence, I mean, the unit of the occurrence would simply be the sum of their probabilities, right? Let me just, because it's a recall, let me just bring it to the fore. Let me rewrite it here just so that we can use that to establish our proof. Okay, and so that's why all these various concepts are important, because they build upon each other, right? Sometimes if you want to prove a particular law, you would need to leverage some other law or sometimes several laws put together in order to arrive at a particular justification. So let's just do a quick recall. So recall. Okay, this is the special additive law. All right. There's a corollary of the special additive law. Right? So it says that for a set of mutually exclusive events, AIs, with I being 1, 2, all the way to N, right? The probability of A1 union A2 union all the way to AN, okay, is essentially the sum of the various probabilities. Right? Or so we can say that this is a big union of the AIs, I moving from 1 all the way to N, is the same as the probability of the AIs, and we're summing them. All right, from 1 all the way to N. Okay, but of course, if they are not mutually exclusive and they have overlaps, it means that this rule does not hold. Then you need to use the general additive law. The general additive law is still the summation, but you need to take out the probability of the various intersections. But here, the AIs are mutually exclusive, so we can just go with a special additive law. All right. So now think about it. Think about it. Hence, so now we're continuing with our proof. Hence, by the corollary, okay, by the corollary, what happens? It holds that. So this is it. We can apply this corollary to now finding the probability of B. Okay. So think about it. The probability of B okay, will become what? The probability of this big union. All right. I moving from 1 all the way to N. Right. So I moving from 1 all the way to N of AI intersection B. Then I close the probability. Right. By this corollary, what happens? It means that this becomes the sum. All right. Here, keep in mind, here we're taking the union of AIs, but here we're also taking the union of some AI intersection B. If it's confusing, we can represent the AI intersection B by, let's say, CI, so that it's straightforward. But I mean, we can still see through, right? So here it means that it becomes the sum of the probability of what? The AI intersection B. Okay, we're summing from 1 up to n. And there you have it. This is the proof. All right. Right. So we've been able to establish this claim. So in fact, the main theory of total probability is now what I'm about to state, right? I had to write this out fast because we need this to establish the law of total probability. Okay, so let's just do that together. So now we have another theorem, a second theorem for the day. So theorem, and please do all to number the theorems, okay? Just so that, I mean, we've taken a look at several theorems, and I think at a point you lose track of the numbering, so that one can easily make reference to them. So there's another theorem, but this is the total probability theorem, right? Very, very important in probability studies. So total probability. Good. What does it say? It says that suppose suppose a AI, okay, where I moves from 1 to n, okay, is a partition. So A1 is a partition, A2 is a partition, all the way to AN is a partition. That's what it means. So suppose AI forms a partition. Forms a partition of omega. And the events B right, is defined on the same sample space. All right, such that the probability of B is positive. Because then if the probability of B becomes 0, then we don't even have a conversation to have in the first place, right? So there has to be a positive probability. Okay, then it means that we can make this argument. The probability of B can be written as the probability of A1 multiplying the probability of B given A1. So now we're invoking conditionality here. Okay, plus the probability of A2 multiplying the probability of B giving A2. Plus all the way to the probability of A n multiplying the probability of B given an. And we can write this in a more succinct form as the probability of AI the probability of AI multiplying the probability of B given AI. All right, and then summing this. This is it. So in the previous case, we studied that the probability of B, okay, can be written in this form. But the total probability rule says that, yes, that same probability of B can also be written as the sum of the sum of the product of marginal probability and a conditional probability, right? And the proof is very straightforward because we've done a major part of the heavy lifting in the previous proofs that we've considered. But again, even if you look at this very closely, you can see that there's a linkage between this and the past session that we had. I think it was on the multiplicative law, right? Because it's only the multiplicative law that allows us to write the probability of an intersection in terms of what a conditionality, right? So let's establish the proof. Good. So you recall from I think it's I think it should be the general multiplicative law, right? So recall So because these are recalls, let me just go back to use my red. Right. So recall from the general, which is just what we looked at in the previous meeting, right? So recall from the general multiplicative law. And what does it say? That law says that the probability of A intersection B, okay, is given by the probability of A multiplying the probability of what B given A. If you like, you can also write the other way around. So you can also write the probability of B multiplying the probability of what A given B. This is what we studied in the previous meeting, right? Also recall from this recent theorem, right? Just this recent theorem. All right. Also recall from recent theorem. And that's why the numbering of the theorems is important so that we can be a lot more specific, right? So recent theorem, right? Let me just call this one because it's the first theorem for the day, all right? So theorem one. And let me call this theorem two, right? So from recent theorem one, we've also just established that the probability of B is equal to this, right? Probability of A I intersection B. And then we sum. Good. So in order to establish this total probability law, okay, or this total probability rule, right, we just simply need to combine these two theorems, right? It just follows trivially. Okay, so hence, what needs to happen? If we substitute this, all right, let me call this one, and then let me call this two. Right? If I substitute this into this, it just gives me what I'm looking for. All right. So hence, it means that, but you see here, I just made use of A intersection B, right? I could append the I's as well. Okay, so let me just do that. So And when we looked at the general multiplicative law, we did not look at partitions, but it's just the same principle. All right. So if the probability of A intersection B is given by this, then the probability of AI intersection B is also given by the probability of AI, and so on and so forth, right? It's just a notational difference. Okay, so let me just quickly add that. So I, and then I could also have I here. Okay, so hence, by substituting one into two. Okay, substituting one into two. It holds that the probability of B, okay, is equal to the sum of probability of AI intersection B, which is now equal to, so wherever I see probability of A intersection B, I can just replace the top part, right? In fact, I can also replace the bottom part, meaning that this total probability rule we can state it in two different ways, depending on what we're placing focus on, but they would all give us the same probability for B, all right? So let's just, because I've stated it using the top part, let me just use that. Okay, so this is the same as the sum all right? The sum of this probability is the same as the sum of the probability of AI multiplying the probability of B given AI. And although I haven't stated this in the theorem, this can also be equal to, so let me put that in red. This can also be equal to, so I can also say equivalently, I can also say that the probability of B, which is equal to this, right? I can also write it as the summation from 1 to n. This time around, I can use the second part. But you see, and let me just mention this. The reason why, I mean, that will be accurate, but that doesn't really, is not relevant, because think about it. We're interested in finding the probability of B. Okay, so if I say the probability of B is the same as the sum of the probability of B multiplying probability of A given B, it's like you're using, you need to find a certain value, and you're using the value itself, which you do not know, to find itself. It's like a secular argument that we're making, right? Although in principle, supposing that you had values for the probability of B, and you have like a left-hand side of the equation and then a right-hand side of the equation, necessarily the two sides must be equal, okay? But here in principle, in theory, it makes a lot more sense to find an unknown to find a value using some other unknown values or some other known values for that matter. Okay, so that's how come we are skipping the second part, but it still is an equivalent expression, right? So we're saying that to find the probability of B, we can use, if we know the probability of AI, we can use it. And if we know the probability of B given AI, we can also use it. Keep in mind that the probability of B is not the same as the probability of B given A. They are two different quantities. The probability of B given A is a conditional probability of B given A. And the probability of B is simply what we call the marginal probability, okay? Just a strict probability. All right, good. Right. So that establishes the proof, okay, by we recalling some important theorems and just making some algebraic substitutions to be able to arrive at the required conclusions. Right. Just a quick example here. So giving this proof, right, let's take a look at this quick example, right? A delegation to the Accra Technical University, ATU, comprised 20 students from the University of Ghana, UG, and 25 students from the University for Professional Studies, UPSA, both in Accra, Ghana. Among the students from UG, 13 were females and 10 females also came from UPSA. If a student was chosen at random to deliver the opening remarks, what is the probability that this particular student is a male? Okay, so let's figure out how we can go about this. So, of course, there are several ways of approaching this, but I would want us to apply some of the principles that we've just looked at in this meeting. Good. So let's consider the following events, right? So we're creating our own events, right? So let me call my first event UG. We could call it A, B, C, and so on and so forth, right? But I just want to make it a lot more practical. So let's say that my first event, I'm calling it UG. All right. So this is the event that a student is from University of Ghana. All right. Then let me define a second event. Let me call the second event UPSA. Right. So a student is from the University for Professional Studies. Okay, good. Then let me also define another event. And I'm defining all of these based on the cues that the problem is giving us, right? So we're told certain number of students were females in the problem. Okay. So F is, so a student is from UG, a student is from UPSA, a student is female. Okay, good. Then what this simply means is that either the female students came from UG or the female students came from UPSA, right? It has to be one of these. Or if I want to frame it, either the male student that was chosen came from the University of Ghana, or the male student chosen came from the University for Professional Studies. Okay. But you see, this is the union of two disjoint events. Okay. Which I can write as UG intersection F and UPSA intersection F. So let me write it down. So from the preamble, from the problem, right? From the scenario. From the scenario, either a female student comes from UG or a female student comes from UPSA. So the point that we're making is that if you take a female student, right, out of the delegation, if you take a female student, it is not possible to say that, okay, you're a female student, you come from UG, and at the same time, you come from UPSA. It's not possible, right? You have to come from either one of them, right? So that's what I'm saying. So let me write it down. So this is the union. This statement, okay, this either this or that, okay, because whenever we talk about or, we're taking the union. So this is the union of two pairwise disjoint events. Okay, or I can just, because here there are just two cases, so of two events, of two disjoint events. And what are they? Which are, so we're saying what? UG intersection F. Okay, are you following? The UG intersection F and UPSA intersection F. All right, that's the argument that we're making here. So then, though the problem is saying that let's find the probability of a student being male, okay, but we can, based on the problem, try and find the probability that the student is female, and then afterwards we can worry about males because we've been given data point on females, okay? So thus, we can say that the probability of being a female is, so here I can apply what we have just looked at, the total probability rule, right? The probability of being a female here is just like the probability of finding B. Okay, keep in mind we have the sample space, and the sample space here is, every member of the delegation, male, female, UG or UPSA, coming to ATU, right? So let's just go back to the diagram just so that we can draw the analogy here. So the A1 here, we have a partition, A1 and then A2. A1 here would be UG, and then A2 is UPSA. Okay, so this whole sample space, the omega will just be a delegation coming from A1 and A2, right? And then the B would be females. Now you see that you cannot come from UPSA and also come from UG at the same time, right? So the UG and then the UPSA are mutually exclusive. And at the same time, they are collectively exhaustive, because if I take the union of UPSA and then UG, it would be equal to the delegation, right? Good. Now, at the same time, you have the female representation intersecting with the UG and then the UPSA, because there are female members of UG and then there are female members of UPSA as well, just as we also have male members. Okay, so you realize that all these principles or these conditions have been satisfied. So therefore, we can apply the total probability rule. Okay, so now the question has asked us to find the probability of a male, but we can find the probability of what a female. And then afterwards, we can just take the complement because it's just binary. Okay, so the probability of finding a female will just be the same as the probability of finding B. Right? So there you have it. So let's just go back. So probability of finding a female would be equal to the probability of UG okay, multiplying the probability of being a female, given that you are from UG. plus the probability of coming from UPSA multiplying the probability that you are a female, giving that you are from UPSA. So here we have two cases. That's why the summation is just two, right? If the delegation were coming from, let's say, 3 schools or 3 universities, maybe I could add KNUST. We would have had 3 summations. If they were coming from 10 universities in Ghana, it means I would have 10 summations. So this could go on and on and on. If they were coming from, let's say, 100 universities in Africa, it means I would have about 100 summations. So my n will be 100, right? That's the whole point. If there are, let's say, 1,000 schools coming from across the world, then so it goes on and on and on that way, right? So here we have just a simple case of 2 schools. So we have 2 summations. So let's go back into the problem and figure this out. So what is the probability of coming from UG? This is just trivial, right? First of all, let's ask ourselves, how many students are even coming in the first place? So we can just apply classical probability, right? So a delegation to ATU comprised 20 students from UG and then 25 from UPSA. So in all, there are 45 students coming, all right? 45 students coming. So the probability that a student is from UG would simply be what? The number of students from UG over the total number of students. So that's 20 over 45. Which can be simplified, definitely, but let's just leave it this way for now. Okay. Now, what is the conditional probability of being a female, given that you are from UG? It comes here. Among the students from UG, okay, so among the students from UG, 13 were females. This is a way of telling you that the conditional number of females, okay, from UG is 13. Because if I say there were 13 females versus if I say there were 13 females from UG, this last statement I made is a conditional statement. Because if I just say there are 13 females, it could be that the 13 females come from any of the schools. But if I say there are 13 females from UG, it means it is a conditional number. And if I have a conditional number or a conditional count, I can use that to find what the conditional probability. Okay, so it means that the number of females from UG is 13, right? Therefore, the probability of the conditional probability of being a female from UG would now have to be the number of females from UG as a proportion of what? The total number of students from UG. So we're not going to find that as a proportion of the entire 45. This is very UG specific, okay, of the delegation that's coming to Accra Technical University, right? So this is 20 on 45, and this conditional probability will be 13 females on how many students are there from UG in general? There are 20. Okay, so that's on one hand. On the other hand, let's take a look at the probability of being a student from UPSA. Going back into the scenario, there are 25 of them. But again, because there are 25 of them, the probability of coming from that institution will be the number 25 as a proportion of the total delegation, the total count of the delegation, right? So that will be 25 on 45. Okay. Similarly, what is the probability of being a female from UPSA? So 10 of them are females. So the conditional probability of being a UPSA female would be what, 10 on 25, not on 45. Okay, so 10 on 25. That's it. So at this point, we can, if you work this out, this just simply becomes 13 on 45. Okay, that's why I didn't even want us to bother to simplify this 20 on 45 because they will just cross out each other. So this becomes 13 on 45, and this also becomes 10 on 45. So 13 on 45 added to 10 on 45 becomes what? 23 on 45. Okay. Hence, because male and females are, they are binaries. I mean, if you take the gender set, it's either you're a male or a female, regardless of what the contemporary world wants us to believe, right? There are two genders, a male or a female. I'm talking about biological genders, right? Just to be clear. So once the probability of being a female is 23 on 45, it means that the probability of being a male, so therefore, right, the probability of being a male would be what? The complement of the female probability. Okay, because the two probabilities need to add up to one. So this becomes 1 minus 23 on 45. And that becomes 22. On 45. And this probability is slightly less than 50%, right? Slightly less than 0.5. Okay, so that should be about, I think 0.4849 thereabout, right? You can verify, but I think approximately 0.49. So there's almost like a 50-50 chance that a female or a male was chosen. But yes, this is our probability. I mean, another way you could have done this is to essentially take the, let's say, among the students, right? You could also have computed the, I mean, because we know the total number coming from all of the various institutions, and we've been giving only the female representation, we could also ascertain the male representation. Okay, so for example, instead of saying that there are 13 females from UG, it's the same as saying that there are 7 males from UG, right? And then instead of saying that there are 10 females from UPSA, it will be the same as saying that there are 15 males, okay, from UPSA. And we can define our events, okay, UG, UPSA, and then define a male event, right? And then we can just apply the total probability scenario, and that should lead us to arriving at necessarily the same value. So there you have it with the approach to this particular problem. Now, once we talk about the total probability rule or the law of total probability, another important law just follows, right? Keep in mind, in this particular example, we realized that a student was selected and we computed the probability that the student was male, right? But because the problem gives us information on females. Let's assume that we were supposed to find first the probability of a female, which is exactly what we did, right? The probability of a female student was 23 over 45. Good. But you see that the female could come from either university or universities, right? The female could have come from UG, or they could have come from the UPSA. All right. And so if you recall this statement, right? We said that the probability of a female is given by this expression, the probability of coming from UG multiplied by the conditional probability of a female plus the probability of UPSA multiplying the conditional probability of a female from UPSA. Now, think about it. So let's assume that we have an additional information, and the additional information says that a female student was selected, right? And we're interested in computing the probability that the student was from UG. Look at the question very well, right? A female student has been selected. What is the probability that the student is from UG? You realize that here we are reversing the process. We are reversing the order of the conditioning, right? You see here, we're talking about the probability. Let me just switch on my, this side. We are finding the probability of being a female, given that you are coming from UG, right? And then when it comes to this side, we're finding the probability that you are a female, given that you are coming from UPSA. The new addition that I am introducing here is, fine, a female student has been picked. What is the probability that the student is from UG? Or again, if a female student has been picked, what's the probability that that student is coming from UPSA? So instead of finding the probability of F given UG, or finding the probability of F given UPSA, how can I find the probability of UG given F? Okay, or how do I find the probability of UPSA given F? At this point, like I said, we're reversing the order of the conditioning, and we call this the Bayes theorem or the Bayes law, or in some texts we call it the Bayes rule, right? Because the person that introduced this rule is called Thomas Bayes. Okay, he was a mathematician sometime in the 18th century. And so it's named after him, Thomas Bayes. So we call it the Bayes theorem. Or as you move further, you would see that there are several theorems named after Bayes. You know, Bayesian in France, Bayesian, etc. Right? He's made some very important contributions to mathematical statistics. Okay, so let's take a look at the Bayesian theorem or the Bayes theorem. Okay. So the Bayes theorem. So there is a specific, I'll just give you a general overview, right? And then we'll state the actual theorem. All right. So So let's suppose so let's suppose there exists a if let's say there is some hypothesis, right? I just want to give like a general introduction. So if there is some hypothesis, and then there is some observed evidence, right? The Bayes theorem is the relationship between the probability of the hypothesis after getting the evidence. All right. So let me just put this out there. So suppose there exists a hypothesis H. Okay. And some observed evidence. And let's call the evidence E. Okay. We're saying that the Bayes theorem so I want to give you a philosophical understanding, and then we'll look at actual theorem. So this is a general philosophy, right? So we have some hypothesis. A hypothesis is a claim, right? A claim that can be verified, all right? A statement that can be verified, whether it's true or false, right? So it's like a conjecture. It hasn't been proven, but we suppose that there may be some truth in it. So, but first of all, we need to test it out to establish its validity. So there's a hypothesis and some observed evidence, right? Then the Bayes theorem, right? The Bayes theorem okay, establishes a relationship okay between the probability right of the hypothesis after obtaining the evidence. Okay, the Bayes theorem establishes a relationship between this probability, okay, and this probability is actually a conditional probability. The probability of the hypothesis after obtaining the evidence is the probability of H given what E, right? So the Bayes principle establishes a relationship between this probability and the and the probability of the hypothesis. Okay, of the hypothesis before, or if you like, without the evidence, right? So that is simply the probability of H. The probability of the hypothesis without the evidence is simply P of H. Okay. So it is given by the philosophical underpinning of the Bayesian theorem is simply saying that the probability of the hypothesis giving the evidence, okay, is the same as this relationship. Okay, the probability of H multiplied by this expression on the probability of the evidence. All right, and we will define what these terms are. Now, while I do that, let's just put this in perspective, right? Let's assume there is a situation, right? Maybe there's a criminal case that's happened, and a hypothesis here would be like a suspicion, right? The crime agency, let's say the police, right? Maybe based on eyewitnesses and like other accounts from people within the neighborhood, there may be some suspicion. So the police or the crime or the detective agency could say that, okay, we can hypothesize or we suspect that the criminals maybe are coming from this particular area, or they come from a particular household, or they come from a particular vicinity. Okay, because maybe as part of the eyewitness accounts, some of the people within the area said, "Oh well, I saw that once they finished with everything, they drove past the side and they went through this direction and so on and so forth," right? Or maybe there are some CCTV cameras on the streets and they were able to record the time that these criminals were speeding away, right? So that is a hypothesis. They've not yet been convicted, so we can't say that they are indeed the ones that committed the crime. It could just be a pure coincidence. Okay, maybe the vehicle that you saw was just an innocent individual who has an emergency, okay, and is driving speedily. It's just a coincidence that around the same time he was driving speedily past the post, the crime also happened. So it just looked like he is potentially the person. Okay, so that's why we're calling this a hypothesis. It's not yet an established fact, but we need to verify. Okay, so if there is a hypothesis and we're calling it H, right? And here our hypothesis is what? A suspicion of a crime. And there is what? Some other evidence. Okay, of course, evidence will be the fact that, well, maybe there's a video of you committing the crime or something, right? Something that gives clear-cut indication that this person or these group of people committed the crime. That's what we call the evidence, the proof, right? This Bayes theorem is helping us to establish that relationship between the probability that the suspicion is true after we have obtained the evidence, okay, because truth can only come or can only be established after there is a proof or after there is an evidence. Before the evidence, everything else is just a hypothesis or a suspicion, okay? So a fact becomes an establishment only after the evidence has been obtained. So the truth here is what we're representing by the probability of a hypothesis giving the evidence, okay? So we are establishing a relationship between what the truth and the probability of the suspicion. So in other words, if we know the probability of the suspicion, how can we use that to find the probability of the truth? Because the truth is what we're interested in, whether it's a criminal case, whether it's a financial case, whether it's a health case, because even in the medical sciences, negligences happen all the time and people unfortunately lose their lives, right? We can apply some of these probabilistic arguments to establish whether it was a case of it was just pure medical accident or it was medical negligence that caused the unfortunate circumstance to happen. All right, good. So before we look at the formal statements, let's try and define what these P of H and the P of HE and so on and so forth are, so that you can appreciate the philosophical perspective before we look at the mathematical implementation, right? So P of H, okay, this is what we call the prior probability, okay? And you see in the preamble, I called it the probability of the hypothesis before the evidence. So this is purely the probability of a suspicion, no evidence. So it's not yet the truth, right? So this is what we call the prior probability. Prior probability. Okay. And it is the initial probability it is the initial probability of the event okay. So the probability of H is simply the prior probability, and it is the initial probability, right? Because I'm using initial and then original in the same sentence, which is a bit tautological, but then just to sort of re-emphasize the point. So it's the initial probability that was originally obtained, right? Originally obtained okay, before any new or additional evidence. Okay. Was collected, right? Then what is the probability of H given E? The probability of H given E, all right, the posterior probability. So the posterior probability, okay, um, and of course this is the probability that the event has been revised, okay, after new information has been collected. So right, it is the probability. It is the probability right? So the probability of H given E is the posterior probability, and the probability of E this time around we're reversing the order of the condition. The probability of E given H, all right, on this. All right, this is the factor. The factor that relates that relates the posterior, right? The posterior probability that relates the posterior. Okay, the posterior probability or the posterior and prior probabilities. Okay, the posterior and prior probabilities. Okay, and we call this the likelihood ratio. Okay, There's a likelihood ratio. Okay, so essentially, if you take a look at the Bayes theorem, it's simply saying that the posterior probability equals the prior probability times the likelihood ratio. Okay, so this essentially means that the posterior, right? And this is a very interesting concept, even very much applicable in our everyday world. That the probability of the truth, okay, can be found by taking the probability of the suspicion multiplied by how likely the suspicion is to be true. Okay, so in essence, the posterior right? So the posterior probability, the posterior I think my writing pad is right. So the posterior probability okay is basically equal to prior probability all right times the likelihood ratio. All right, times how likely this can be true. All right. All right. So this is the philosophical dimension of the Bayes theorem. Let's look at the formal statement. Right? So this is actually a theorem. It's a theorem. And this is the Bayes theorem. All right, let's suppose right? So suppose that, we have some AIs. All right, AI, where I moves from 1 all the way to n. Okay. Are mutually exclusive and collectively exhaustive. Okay, mutually exclusive. And collectively exhaustive. Mutually exclusive and collectively exhaustive events in the sample space. Okay, with prior probabilities PAI. Okay, so the probability PAI is not 0. All right, for of course, for I being equal to 1, 2, 3, all the way to n, right? So all the probabilities of the various partitions are non-zero. All right. Then we can say that let B. So you realize that the preamble or the statement is along the lines of total probability, right? So in fact, after I'm done with the statement, you would realize that the Bayes theorem is really is sort of derived from the total probability principle. All right. So with prior probabilities, PAI is equal to 0. Right. Let B be any event in this, all right, for which right, for which for which the right? So this is the statement of the theorem, right? Suppose that we have some partitions, and I'm calling them partitions because in the problem, we've stated that they are mutually exclusive and they are collectively exhaustive, okay, over the sample space, with their various prior probabilities being non-zero. Of course, when I say they are non-zero, it doesn't mean they can be negative, okay, because there are probabilities here. So obviously greater than zero, but of course bounded on the upper by one. Then let B be any event in the sample space for which the conditional probabilities of B giving AI are as such, okay, where the probability of the B's is also non-zero. So now let's suppose that the probabilities of the AIs and the probabilities of the B given the AIs are known. Then the probability of the AI given B is given by this expression, all right? So the proof is simple. Right? Recall the conditional probability, expression, right? Recall. So once again, let me just use this. So recall. Recall the definition. Okay, the definition of conditional probability. Okay, so the definition of conditional probability. All right, and we know that by that definition, the probability of the probability of AI given B okay, the probability of AI given B okay, is given by the probability of AI intersection B, okay, over the reference probability, so over the probability of B. Okay, there's a standard definition. Now let's look at the numerator. We can replace the numerator, okay, by the theorem, the expression that we looked at just not too long ago. I think like the past hour or so. All right. So we know that the multiplicative rule, all right, the multiplicative rule. So we can write this top part as the probability of A multiplying the probability of multiplying the probability of B giving A, right? So also recall. So there are three recalls that we would make. So let me call this equation 1. Right. So recall the general multiplicative law. Okay. The general multiplicative law. Okay. What does this say? It says that the probability of AI intersection B, okay, will be equal to the probability of AI, okay, multiplying the probability of B given AI. Okay, then also recall, finally, so let me call this equation 2. So recall also, and here I'll just be pulling that from the side. Let's just take a look at this from the total probability rule. Yes, this. We can recall also that the probability of B is given by what? The sum of this probability. All right. So let's just recall that too. Recall also the total probability law. Right. The total probability law. Okay. And what does the law say? It says that the probability of B, all right, the probability of B is the same as the sum okay, so the probability of AI, okay, multiplying okay, AI. So this is 3. Right? So we can see clearly that we're trying to prove this theorem. Okay. So by substituting equation 2 and 3 into 1, we can arrive at the proof. Okay. Hence, by substituting by substituting 2 by substituting 2 and 3 into 1. Okay. We arrive at the expression that we need. Okay, so we have the probability of AI. Okay, the probability of AI giving B, right? The prob of AI given B is equal to, so the top part simply becomes this, right? So probability of AI intersection B becomes this. So the probability of AI, okay, multiplying the probability of B given AI. All right. And all of this on the probability of B, which is equation 3. Okay, so I is 1, N. Okay, so the probability of AI multiplying the probability of B given AI. All right. All right, so let me just write that out properly. Right, but I mean, if you look at this, it makes sense, because if you look at the top, right, if you look at the top very well, it is the same as what you have at the down. The down is the sum of all the several instances of what you have at the numerator, right? You at the top, you have probability of A multiplying the probability of B given A. And you have the same thing, but just that you are summing. Okay. So at the end of the day, it's going to give you a classical probability, right? And that would be the probability of AI giving, B. So there you have it. This is the proof for that. Okay. That'll be just about it. And before we wrap up, the we want to just go back to the earlier example, right? I want us to look at the earlier example, and let's answer the following additional questions, right? So giving this particular example, let's just quickly refer to it again. Yeah. So this example, right? I'll be using the same to illustrate how we can apply the Bayesian theory. Okay, so in the previous scenario that we looked at about the delegation visiting the Accra Technical University, right? We have some new information, which is saying that the selected student is actually a female. What is the probability that the student attends UG and then two attends UPSA? All right. So let's take the first part. Okay. So we want to find the probability that the student came from UG is actually a conditional probability. Okay. So finding the probability that the student came from UG, ask yourself, who is the student? The student is a female. So the probability that the student came from UG here means that we're finding the conditional probability of coming from UG, given that you are female. All right. So that's going to be the probability, because you've been told to consider this new information that the selected student is female. So this is the prior probability, right? Or the prior event. So any new event would be conditioned on the fact that the person that we selected was female. So the probability of UG giving F, given female, all right? And here, you see, so the question is asking you to find this. We can only find this mostly by applying the Bayes theorem. Okay, so you see the Bayes theorem is giving us the probability of a partition giving the subset. And we know that the subset from the previous diagram that we drew, the subset is what? The female, which cuts across. And the AIs here are partitions. Here there are two schools, UG and then the UPSA. When you take their union, it would represent the two schools that visited ATU. All right. So the total probability rule, just to sort of link it up, is giving you the probability of a female strictly, right? Or the marginal probability of a region B, whereas the Bayes theorem is giving you the probability of a partition giving B. Okay, so we're coming to find the probability of the UG partition giving female. So we'll just apply the same expression, all right? So it's going to be here, the probability of UG multiplying the probability of a female giving UG all over, and then we take the sum, right? And thankfully, we found all these probabilities when we solved the previous problem, right? So this is it. This is the probability of UG giving F is given by, this is going to be the probability of UG okay, the probability of UG multiplying the probability of being an F giving UG. Okay, all this over the sum. So we're going to take the probability right? The probability of UG okay, the probability of UG multiplying the probability of F okay, given UG. All right, plus then we interchange. All right. So this is going to be, so let's think about it this way. So here, this over this, okay, and then we sum all the various probabilities. All right. So that should be just about it. Okay, so the probability of UG multiplying the probability of F given UG. Okay. And we're taking the sum. Okay, so how many of these are there? Okay, that's essentially what's happening. So at the top, we should be looking at, so this must also be the probability, right? So there are various partitions. So the first partition, so it's going to be the probability of UPSA okay. Okay, so probability of UPSA multiplying the probability of F, right, giving UPSA. Okay. Yeah. Because at the end of the day, it's simply saying that let's take the sum of all the various partitions, multiplied by the probability of the interest event given that partition, right? And here our n is 2. So we need to just alternate that way. So this is it, right? And we've done all of these already. So this would be at the top, we would have the probability of coming from UG. I think if we take the sum, it's what, 45, right? So I think if I recall, it'll be 20 on 45. Okay. And we're multiplying this by the probability of F giving UG. I think we found that. Let's just go back and check. The probability of F given UG. I think it should be in the problem somewhere. Yeah, so this is 13 over 20, right? 13 over 20. Okay, so now at the top, so this is at the top. At the bottom, we'll just have to repeat this. So 20 on 45. Right? Multiplying multiplying 13 on 20. Okay, so 13 over 20. Okay, so 13 over 20 plus the probability of UPSA if I recall, I think it's 25 over 45, right? I think that should be it. So let's go and fetch these two probabilities, your probability of UPSA and then F given UPSA. So prob of UPSA and prob of F given UPSA. Okay, good. So 25 over 45 multiplying 10 over 25. So 25 over 45. Okay, multiplying 10 over 25. All right. So, I mean, of course, this can become, right, this can be simplified, right? So this becomes 13 over 45 plus, once again, 10 over 45. That is 23 over 45. Okay, so at the bottom we have 23 over 45. Okay, and then at the top here we have 20 over 45 multiplying 13 over 20. So that's what, 13 over 45. Okay, and this simply becomes what, 13 over 23. Okay, there you have it. There you have it. All right. Secondly, number two. This time around, we want to find the probability that the female student chosen comes from UPSA, right? So I'm going to be finding the probability of UPSA okay, given F. Right? And it's going to be the same, a similar expression, except that you see, as for the sum, it doesn't change. The only part that would change is this top. I would have to replace it by probability of UPSA multiplying the probability of F given UPSA. All right, so this is going to be equal to the probability of UPSA right? The probability of UPSA right? The prob of UPSA multiplying the probability of F, all right, giving UPSA. All right. And if you look at it clearly, the bottom would still be the same. Okay. So it's still going to be the same summation, it won't change. So I'll just simply write over 23 on 45. Okay, so it will be the same thing. So 23 on 45. Okay, yeah. So what do we have here? The probability of UPSA multiplying by this. Okay, we'll just pick it from here. That just becomes 25 uh 25 on 45. 25 on 45 multiplying 10 on 25. Okay. All of this over 23 on 45. Okay. All right. So that's 23 on 45. Just wrap up shortly. Okay. So here in this parenthesis, the first one, we have 10 on 45. So 10 on 45. Okay. All over 23 on 45. All right. And this just simplifies to 10 on 23. Yeah. Isn't it interesting that when we add these two probabilities, the probability of coming from UG and UPSA, we get 13 over 23 plus 10 over 23. That's 23 over 23, and that is 1. This shows that indeed UG and UPSA are the only partitions that we have, right? Good. So let's just quickly recap everything that's been discussed today. So still on important theorems and laws of probability. The core of today's conversation has been on the total probability law and then the Bayes theorem, right? We began by looking at a precursor theorem to sort of help us to understand the issues of mutual exclusivity and collective exhaustivity. These two conditions are required for us to consider a particular region as a partition. Then we established that, okay, by using that figure, and then of course recalling certain important laws that we've looked at, particularly the special addition law of probability. Then we leveraged that to properly establish, to formally establish the total probability. Okay. The fact that you can find the probability of, you can find a marginal probability as the sum of the product of a marginal probability and the conditional probability. We've looked at the proof as well, and we looked at an example of a delegation that's coming over to a Technical University. Then we moved on to Bayes' theorem, and we looked at the philosophical underpinnings of it, right? The idea of a hypothesis and evidence, and the idea of the posterior probability being the the probability of an event after some new information or evidence has been found, and then the idea of a prior probability. And we said that the probability of the ratio of the probability after the evidence has been found to the probability before the evidence is what we call the likelihood ratio, right? So in other words, the probability of the truth to the probability of the suspicion is the likelihood ratio. Because the suspicion is a mixture. A suspicion can be true or false, right? But the probability of the event giving some new information is the truth. All right. So when you take that ratio, it becomes the likelihood ratio. Then we've established, actually, I mean, in formal terms, the base probability, and we've proved it. Okay. Just recognizing the fact that it comes from we utilizing the definition for conditional probability and applying the general multiplicative law and the total probability by substitution. And that results in the Bayes rule or the Bayes theorem. And we've revised our problem set by attempting to find what if we know that you are a female or you are a B, but we want to use that to find which partition do you come from. What's the probability that you come from partition A1 or A2, respectively being UG or UPSA? And we've established that. And the results clearly indicate that they are mutually exclusive and collectively exhaustive. So that brings us to the end of our conversation for total probability and Bayes theorem. I look forward to the very next meeting sometime soon. So, as always, thank you.